Welcome to our Unit 5 review. Now, Unit 5, the chapter is essentially mastery of the laws of exponents, the laws of logarithms, and growth functions. So you become an expert at this stuff, and this is really, really easy. And the applications of this becomes endless, okay? And also your mastery of the laws of exponents and the laws of logarithms, those are huge in advanced mathematics at the college level. It's got to be automatic. So let's get started. Give a general expression for a value on a piece of property t years from now if its current value is $150,000 and property values are increasing at a rate of 9% per year. Key thing right here. 9% per year. All right, what kind of growth function am I going to use? So let's talk about all our growth functions. We'll put them all on this very first slide. The first growth function we have, it's most simply applied with simple interest problems, or that's interest that is compounded once per year. All right, and that looks like a of t equals, you always have, what are you starting with? A sub 0 times your growth factor, which we call that 1 plus a growth rate, or 1 plus r, to the t power. Again, so this is when things are compounded once per year. All right, now half-life, double life. Well, okay, and we go half/double because the applications of this formula are most often used in science when we're dealing with a half-life, or in business when we're thinking about how long would it take my money to double at this interest rate. Okay, so let's go. A of t equals, and you're going to notice a common thing. You always start with something, a sub 0, times, and then you have a base. And this base, well, that's the half double right there. If I want a half-life, I'm going to make b 1/2. If I want a double life, I'm going to make a b2. And that will be to the t over k power, where k is the number of units in time that it's going to take to multiply a sub 0 by b. Very cool. Now compound interest looks very similar to simple interest except for one thing. Again, you always start with something, a sub 0, and now this growth factor actually becomes 1 plus, but instead of just a growth rate, because we're compounding once per year, we're going to take that growth rate and put it in our numerator and then divide that by a k, the number of times we're compounding every year. And then that will be to the k times t power. K times t, because hopefully we're making that investment for several years. And then finally, continuous change. Continuous change occurs in nature. The easiest way to picture it is things like, okay, a plant grows continuously, all right? And the formula is very simple, and this is where we developed our understanding of E, the irrational number E, but it is P sub 0, all right? And they use a P there. You could be using an A there, but it's mostly P for like principal, all right? Your investment, all right? And if we used an A right there, we couldn't call this formula PERT. All right, but it's P sub 0 times E to the RT power. And this is your continuous change model. Okay. Now, in this problem, we're only compounding at 9% every year, so we're going to use simple interest. All right, so let's go ahead. And let me read the problem one more time. Give a general expression. They only want an expression. So honestly, what they don't want the a of t equals, and if you put it there, that's fine with me, but they really just want this part right here. What's my expression? So let's fill in the blanks. A sub 0, what are we starting with? On a piece of property t years from now if its current value is $150,000. And there you go. All right, and then I need my growth factor, 1 plus r. There's my 1. Now what's my growth rate? It is 9%. So I have to add 9% to my 1. All right, and I do that. 9% as a decimal would be 0.09. So that's going to be 1 plus 0.09. And most people want to write that like that. You could put 1 plus 0.09 in there if you wanted to. And that is to the t power t years from now. And there is my expression right there. These growth functions are very, very useful. Number 2. All right, so again, this looks like just a little practice with your laws of exponents right here. Evaluate the following, okay? This is just simplify, simplify, simplify. All right, so there isn't just one way to do any of these problems, all right? So as long as you are using your laws of exponents appropriately, you will always get these problems right. So I like to say there isn't just one way to do these problems, just don't break the law. And I'm trying to be cute there, and what I mean is don't break these laws of exponents. Okay, so I'll try to do this in what I think is the clearest and most concise method. So for part A, okay, well, as soon as I see 2 to the 5th times 2 to the negative 4, I think common base is I add those exponents, and that would become 2 to the 5 plus negative 4, or just a 2. And all I did was use this very first rule right there. So there's my 2, or 2 to the 1st, and then the 2 to the negative 2. Now remember, for an expression to be simplified, it cannot have negative exponents nor power of powers. All right, so if we want to drop this negative exponent right here, we would do what? We would bring it up. So 2 to the negative 2 in a divisor comes up to a numerator as 2 to the 2nd. And then here we are back at number 1 again. B to the x times b to the y equals b to the x plus y power. So that's simply going to be 2 to the, well, x plus y would be 1 plus 2, 2 to the 3rd, and 2 to the 3rd equals 8. And that's how you simplify these expressions using laws of exponents. Now, part B. Man, negative exponents all over the place, but the key is when I have grouping symbols to a negative exponent outside the grouping symbols, I always know I need to somehow make whatever is within the grouping symbols one fraction that I can take the reciprocal of to drop my negative on the outside. So let's see if we can make 5 to the negative 2 plus 5 to the 0 into one fraction. And you all agree that 5 to the negative 2 would be 1 over 5 squared, which I'm going to write as 1 over 25. And then 5 to the 0, well, anything to the 0 is 1. And to get a common denominator, can I write that 1 as 25 over 25? And now, hey, two fractions, common denominator, let's add them. So 1/25 plus 25 over 25, that'd be 26 over 25, and 26 over 25 to the negative 1 power. Well, to drop that negative, I just need the reciprocal of this fraction, so that's going to equal 25 over 26. And there's part B. Now part C. Well, underneath this radical, we have 4 to the 6 over 2 to the negative 4. All right. Now, the first thing I would want to do is drop the radical. All right. And can't I write a square root as a rational exponent of 1/2? Just like that. And now I can use all my laws of exponents there and clean this up. Now I'd be thinking, well, this is power of a power. So 4 to the 6th to the 1/2 would be 4 to the, and now we multiply those, power of a power, 6 times 1/2 to the 3rd. And then 2 to the negative 4th to the 1/2 would be 2 to the negative 2. Now this can simplify if I get common bases, and 4 is a base 2 number. So 4 I could write as 2 squared. So what do I have here? If I picture this as 2 squared to the 3rd, that's power of a power again. 2 squared to the 3rd, that'd be 2 to the 2 times 3 power, that's 2 to the 6th. And then I just have this negative exponent I have to get rid of down here by bringing this up. So I'm going to end up with a 2 to the 8th, because 2 to the 6th times 2 to the 2nd, 2 to the 8th. And what is 2 to the 8th? Well, I would double check this on a calculator, but I think 2 to the 8th is 256. Look at that, right on. Okay, so last one here. Now again, I have two terms over one term. I know I'm going to write this as two separate fractions and simplify. So again, two terms with common bases. Let's try to write this fraction as two separate terms with common bases. So let's put that plus right in the middle of things right here. And then my first term would be 3 to the negative 3 over 3 to the negative 3. Easy enough. My next term would be, well, 9 I can write as a base 3 number. That would be a 3 squared to the negative 2. So 3 squared to the negative 2, power of a power, that'd be 3 to the negative 4. And that's over my 3 to the negative 3 again right there. And now let's clean up both of these. Wow, how do you guys want to write 3 to the negative 3 over 3 to the negative 3? I think I'm going to forget about common bases for a moment and say that's 1. Yep. And then I just looked at the magnitude of my exponents when they're both negative. Which one has bigger magnitude? That's the one I'm going to move. It looks like 3 to the negative 4 is a winner, so that is going to have to come down as a 3 to the 4th in my divisor, leaving a 1 in my numerator. All right, and then I see 3 to the negative 3 times 3 to the 4 in my divisor. All right, and isn't that rule number 1 again? 3 to the negative 3 times 3 to the 4 would be 3 to the 1st, or 3. And what do we have? We have 1 1/3, and you will probably want to write 1 1/3 as 4/3. And there you go, number 2. Oh, this is cool. Number 3, solve each equation. Well, this looks like an opportunity for us to get common bases, because these are exponential equations. And before you studied logarithms, the way we undid exponential equations is to get common bases. And these would be kind of a little more complicated to actually do with logarithms. So let's check it out. Base 2, base 4. Well, base 4 is a base 2 number, so that's the direction we're going to go, common bases. Okay, and use those laws of exponents, you guys. All right, so I see a 2 to the 6 minus 8, and on the right, that 4 is actually a 2 squared. So again, we're using this number 1 again. Boy, we use that a lot. Excuse me, we're using power of a power down here, number 7. All right, so we have a 2 to the 2nd to the 2 plus 6. Or I should say 2 to the 2nd to the 2 plus 6 power. So I'm going to multiply those exponents. So if I distribute a 2 to 2 plus 6, I'll get a 4 plus 2x. I hope you all see that. And now we have common bases. So if 2 to the 6 minus x equals 2 to the 4 plus 2x, that can only be true if those exponents are equal to each other. 6 minus x has to equal 4 plus 2x. Now, let's skip a couple steps here, but I would add x to both sides to get a 3x on the right. And then get rid of that 4, subtract the 4, so 6 minus 4, 2 on the left. So x equals 2/3. Great. Now, same thing here. This looks like it might be a little more complicated, but really it's not. Common bases again, right? Okay, so this factor of 3, think of as 3 to the 1st. And what's the square root of 27 if we write that base 3? Well, isn't 3 to the 3rd 27? And isn't a square root a 1/2 power? So wouldn't that just be 3 to the 3/2? Yeah, equals. And then 9 is 3 squared. 3 squared to the 2x would be 3 to the 4x. And there's my common bases. Now let's clean up the left a little bit. So 3 to the 1st times 3 to the 3/2, we add those exponents. So 1 plus 3/2 would be 2 over 2 plus 3 over 2. That's a 5 over 2. All right, and now we have common bases. We have an exponential function with common bases, and the only way this can be a true statement is if 5/2 equals 4x. Divide both sides by 4, And you're going to get x equals, well, 5/2 divided by 4 would be 5/8. Wonderful. Number 4. A gallon of milk costs $1.99 2 years ago. Now it costs $2.19. To the nearest percent, don't forget that, round our answer to the nearest percent, what has been the annual rate of increase in the cost? So annual rate of increase, that tells me again, simple interest. We're only compounding once per year. All right, and a little review of that. It is A of t equals a sub 0. What we start with, in this case, that's $1.99, times our growth factor, which is our 1 plus r, and they want us to solve for this r, and then that's going to be to the t power. There it is right there. So let's put in what they gave us and solve. So we start, milk was at $1.99. That's my a sub 0 right there. And then times 1 plus r to the, how many years ago? 2 years ago. So this is going to be a 1 plus r to the second. Now it costs $2.19. So this expression has to equal $2.19. And again, to the nearest percent, what has been the annual rate of increase in the cost? So they didn't give us a rate, so we're 1 plus r, and we're going to solve for that rate. So now it's just simple algebra. Well, first thing I would do is divide both sides by $1.99. So on the left, I have $2.19 divided by $1.99. And on the right, I am left with that quantity 1 plus r to the second power, my growth factor to the second power. Now I have to get rid of that exponent, so let's just square root both sides. Square root of, and I know usually when we take a square root we have to talk about the positive and the negative root, but the negative does not apply in the story problem right here. And if I take the square root of 1 plus r to the second, that's going to leave me 1 plus r. And now, one more step, subtract r. Or excuse me, subtract that 1. We want to solve for the r. So r equals the square root of 219 over $1.99 minus that 1. And then we're just going to punch that out and make sure we round our answer to the nearest percent. So I'm going to get my calculator out. You guys punch this out with me. Let's all punch it out together. And again, you know, there's some parts of this test where your calculator is very appropriate, but you got to practice it because it's easy to make a mistake on a calculator. So I'm going to go to square root of 2.19 divided by 1.99 minus 1, and that is on my calculator. Later I have 0.04904838843, and they want that to the nearest percent. 0.049, I'd call that approximately 5%. There you have it. All right, number 5. Graph y equals 2 to the x power. This is a simple exponential growth function right there. Okay, so when I see this, it should be like graphing a line to you. You already see the y-intercept, I hope, because that's 1 times 2 to the x. So we're starting with a y-intercept of 1. And because this base is greater than 1, you know this is going to be exponential growth. Now I know I have all these pretty hash marks, but I'm just going to rough out what does exponential growth look like. Something like that right there. Okay, now, and then they would like y equals 2 to the negative x. Okay, so what does that look like? Well, if you can graph y equals 2 to the x, then you should be able to see the graph y equals 2 to the negative x, because we have that same 1 times 2 to the negative x, same y-intercept, and the only thing that changes, x has become negative x. Now, isn't that a reflection in the y-axis, excuse me? So let's reflect in the y-axis. There you go. There's the two graphs. So graph y equals 2 to the x and y equals 2 to the negative x on a single set of axes. Got that? How are the graphs related? Well, we just verbalized that. Y equals 2 to the negative x is a reflection in the y-axis I hope you clearly see that, of y equals 2 to the x. Okay, number 6. Explain how p of t equals p sub 0 times 1 plus r to the t. Now again, this is my simple interest formula right here, but they're using p instead of a, and that's very common in the business world because they're talking about p is like the principal of my investment, what I invested, and then we're hoping every year that that is growing. So explain how p of t equals p sub 0 times 1 plus r to the t can be used to model exponential growth and decay. Give an example of each. Well, it's all based on that growth factor right there. And you guys understand, we just saw that on the last problem. When we had base 2 is bigger than 1, so that gave us exponential growth. All right? So here, if this growth factor is a number greater than 1, we're going to have exponential growth. So, growth factor, it's all about it, and growth. Well, if 1 plus r is greater than 1, that implies we will always have exponential growth. And an example of that. Well, remember the very first problem in this unit was that burger problem? There it is, yeah. We had the $4 burger that was going up in price by, I believe, 9% every year, so our growth factor was 1.09. Now, that's not a whole bunch greater than 1, but it is greater than 1, which means this is an example of exponential growth. Every year, the cost of that burger gets higher and higher. Okay, how about decay? Well, again, if the growth factor, that 1 plus r, is between 0 and 1, we will have exponential decay. So here it is right here. Throw the growth factor right in the middle right there. 1 plus r. So if 0 is less than my growth factor and my growth factor is less than 1, we will always have exponential decay. And we had a few examples of that. Remember the calculator problem and the truck problem? Well, looks like I used the truck problem because there's a lot of a sub 0, or in this case, c sub 0 right there. Yep, there it is. The 2000 and I forget, what is that, a 2003 Dodge Ram. I still remember this moment, and what a beautiful day at the beach. Okay, so let's see. What did we say the truck was worth? Hopefully a little more than that in this picture, because I just spent a whole bunch on it. But they said a truck was worth $8,200. And wasn't the rate R equal, wasn't it dropping in value by 20% every year? So that would make my growth rate 1 plus negative 0.2. which is 0.80. Ouch, that hurts. And there it is. There's an example right there of exponential decay. Number 7. All right, here. Now we're going to make money. We're not losing money on a truck. We're going to make money on an investment. So, number 7. Suppose that $1,500 is invested at an interest rate of 8.5%. Nice. How much is the investment worth after 18 months if its interest is compounded quarterly? Very common here. Or continuously. Now that usually doesn't happen with, investments continuous. That's usually in nature, but hey, let's take a look and see what happens. So, we're compounding, so let's start off with first, what is our compound interest growth function? Compound interest. A of t equals, and again, we always start with something, a sub 0, and then we have not 1 plus r, but 1 plus r over k, where r is our growth rate, and k is the number of times we get to compound every year, and that is to the kt power right there. Beautiful. All right, so in this problem, P of t equals, well, we invested $1,500. There's my $1,500. And then my base becomes 1 plus, and what's my growth rate? 8.5%. Let's write that as a decimal, 0.085. And quarterly means I'm compounding 4 times per year, so this k is a 4. And that will be to the k times t power, which I will say is a 4t. And there's my formula right there. Now, let me see. What is this investment worth after 18 months? Hey, don't throw an 18 in for that t there. That'd be 18 years. What is 18 months? That would be 1.5 years. So we need p of 1.5. So we get our calculator out and let t equal 1.5. So I'm going to very carefully go 1,500 parenthesis 1 plus 0.085 divided by 4, close my grouping symbol, to the, and now when I go 4 times 1.5 right here, if I don't want to do that arithmetic, I'm going to put this power in parentheses, to the parenthesis 4 times 1.5, close that parenthesis, and you could have gone 4 times 1.5. Isn't that just 6? But anyway, there it is, and I always double check my calculator. 1,500 times the quantity, 1 plus 0.085 divided by 4 to the 4 times 1.5 power, and I put that 4 times 1.5 in parentheses, and I have $1,701 and approximately 70 cents. Oh, look at that. Nice. Now, continuously. Well, I know compounding continuously. We're not going to use this compound interest because as soon as I see continuously, I'm thinking nature and I'm thinking continuous change. And that would be simply my p sub 0 equals, or here I'm going right to the expression, excuse me. So p sub 0 equals e, p sub 0, let me say this right, you guys, I'm sorry. Continuous change, the expression is p sub 0 times e to the RT power. There we go. All right, so let's just put this together over here. So p of 1.5 equals, and p sub 0 is that initial investment, 1,500, times e. Remember when we developed e, that's approximately 2.718. But on your calculator, make sure you use that e button to get a much more accurate approximation to the, and then I have my interest rate times time. The interest, make sure you put that in as a decimal, 0.085, and time was 1.5 years. Now let's carefully punch this one out again. And notice here, notice my parentheses for the exponent. A very common mistake is people go 1,500 e to the 0.085 and then they just say times 1.5, and that changes everything. So make sure your exponent here with 2 factors is in parentheses. 1,500 second e to the parenthesis 0.085 times t, which is 1.5. Close that parenthesis. I always look one more time. 1,500 e to the 0.085 times 1.5. I think we have a winner right there. Now, and I know I'm right now because look at what I have right there. $1,703.98. Now take a look at these 2 answers here. Okay, this was quarterly and this is continuously. Doesn't it make sense that continuous growth should give me a slightly higher output than quarterly growth? Something compounded quarterly? And there you go. Now, if you give me 2 answers here, and those are far apart, that would tell me you don't really understand this concept. So make sure your answers are making sense. Number 8. Given that the common log of 25 is approximately 1.3979. Find the value of A, the common log of 2.5. Now you guys, again, okay, if we're in the classroom, this would be non-calculator right here, all right? Now, you're doing this stuff at home, So I know how tempting it might be to just break out your calculator and punch out the common log of 2.5. But please, show me you understand your laws of logarithms. Show me the work here. And you know what? At home, if you break out your calculator to check your work, that's fine with me. That's what I would do too. But I would make sure I understand my laws and logarithms. I would make sure I can do stuff like this without my calculator. Now take a look. It's so cool. The common log of 2.5. Well, I do not know what that is. But here's what I do know. They gave me the common log of 25 is approximately 1.3979. So can I write 2.5 in terms of 25? Hey, thank you. Sorry, my wife just brought in lunch and oh, it looks good. But I promise I'll finish this video first. Okay, thanks, swear. So let's see if we can do that. Do you agree? Yeah, we're going to use you. Okay. The log of 2.5. Can I write this in terms of 25? Well, isn't 2.5 nothing more than 25 divided by 10? Now, I did that because they gave me the common log of 25. So now, let's use these wonderful laws of logarithms right here to write this common log as the difference of two common logs. And all I'm doing is using rule number 2 right here. The log base b of m over n equals the log base b of m minus the log base b of n. So there's my minus. And on the left, I have to have the common log of 25. And on the right, I have the common log of 10. Now, you might be thinking right now, well, how does that help me? It's all based on what they gave us. They told us the common log of 25 was 1.3979 minus, and you guys can do the common log of 10 in your head because, again, 10 to the what power will give me a 10? The common log of 10 is nothing more than 1. So 1.3979 minus 1, and my answer is 0.3979. Oh, it's beautiful. Now, the next one. And look at the common log of 2,500. Do you notice they're giving you a number you can write in terms of that 25? So the common log of 2,500, I'm going to write that as the common log of, well, 25 times 100. And there we go. Now I get to use number 1 up here. The log base b of m times n equals the log base b of m plus the log base b of n. So let's go. We're going to write one common log as the sum of two common logs. And my term on the left would be the common log of 25. My term on the right would be the common log of 100. And we know what the common log of 100 is. And they gave us the common log of 25, so we are essentially done here. The common log of 25 is, again, my 1.3979 plus, and the common log of 100, so that's base 10, so I'm thinking to myself, 10 to the what power gives me 100? That would be 2. So 1.3979 plus 2 would be 3.3979. Oh, I love these problems. Look, Mom, no calculator needed too. Ooh, look at this one. How are we going to write 0.04 in terms of 25? Well, this is why when you were in middle school, your middle school teacher wouldn't say, okay, how do we say 0.04? And don't say 0.04. Isn't 0.04 4 hundredths? And doesn't 4 over 100 reduce to 1 over 25? And there it is. And now I get to use rule number 2 again. So the common log of 1 divided by 25, I'm going to write that as the difference of two common logs. And my common log on the left would be the common log of 1. Oh, I love that. Minus, on the right, the common log of 25. And you guys, 10 to the what power will give me a 1? That has to be a 0. So there's my minus. I have a 0 on the left. And the common log of 25, they gave me approximately 1.3979. So that will equal negative 1.3979. That's 3 very cool problems right there. Okay, number 9. Oh, this is too easy. The log base 2 of 8. You know, to answer these questions, you have to understand what we're doing right here with things like the common log of 100, 10 to the what power is 100? 2. Well, let's do that here. 2 to the what power is 8. Again, it's just a definition of what a logarithm is. 2 to the third power gives me 8. Part B, 8 to the what power gives me 2. Well, some people might panic a little bit here, but think about that. Isn't the cube root of 8 2? And isn't a cube root a 1/3 power? 8 to the 1/3 power is 2. B is 1/3. Now they're getting really cute right here. Oh my gosh, 2 to the log base 4 of 64 power? Well, let's start with our base 2, and we better simplify the log base 4 of 64. So you're thinking 4 to the what power will give me 64? Isn't that 4 to the third? So the log base 4 of 64 is 3. And by the way, if you don't see that, you could get this on your calculator with change of base, but we'll get the change of base a little bit later. Anyway, what's 2 to the third? 8. I love number 9. Number 10, express y as a function of x. Oh man, so here we have this logarithmic equation with common base 2 on both sides, and they want us to write that as y equals something in terms of x. Okay, well, this 2 right there, that's the key. Laws of logarithms. We need logs with common bases, and we have that, but we have a 2 out front on the left, so let's undo that. Can I make this coefficient of 2 an exponent of 2x? So on the left I have the log base 2 of y, and on the right I'm going to write this as the log base 2 of, and if I take 2x to the second power, all right, 2 to the second power is 4, and the x to the second power would be x squared. So again, if the log base 2 of y equals the log base 2 of 4x squared, what does that tell us about the y and the 4x squared? All right, and do I see that down here somewhere? There's my plus, there's my minus. Okay, yeah, right here. If the log base b of m equals the log base b of n, well, that's going to be true if and only if m equals n. The log base 2 of y equals the log base 2 of 4x squared. That's only going to be true if that y on the left equals the 4x squared on the right. Okay, now we've got to figure out for part B, we need to be able to write this as 1 log base 2. So the key is this 2 right here. Can I write 2 as log base 2 of another number? Yeah, because I need common bases. So I'm thinking to myself, log base 2 of what equals 2? Well, isn't 2 to the second power going to give me a 4? So I can write 2 as the log base 2 of 4. There it is right there. And now, again, see this plus right here? We're using number 1. The log base b of m times n equals the log base b of m plus the log base b of n. So now I can write the right-hand side of this logarithmic equation as 1 log base 2, and that would be the log base 2, and we now multiply the 4 and the x of 4x. And if the log base 2 of y equals the log base 2 of 4x, that can only be true if and only if y equals 4x. Awesome. Number 11, express each of the following in terms of the log base b of m and the log base b of n. Oh, wow. Okay. All right. Well, we better get rid of that cube root right there. And isn't the cube root the equivalent of a 1/3 power? So let's go log base b of m squared over n to the 1/3. Now, laws of logarithms. We can bring this power of 1/3 out as a coefficient. So 1/3 log base b of m squared over n. Excuse me, my pup wants out and she's going to have a fit if I don't open the door. I will be right back to everybody here. Go ahead, Rox. Go have fun. Okay, I'm back. Sorry for this real world situation, recording at home and dealing with family and lunches and wives and kids and dogs, but that's the way us teachers live. So 1/3 log base b of m squared over n. Okay, now I got to think about a log of something over something. What can I do there? Well, let's leave that 1/3 out front, and then because I'm dividing, that's my minus right there. And what am I going to put out front right here? That would be the log base b of m squared. And I'm just using, again, rule number 2 right here. And then right here would be the log base b of n. Now, I am almost done, except they don't want this m to be squared. So what can I do with this exponent? And that is number 4 there. It comes out front as a coefficient. So I'm not going to get fancy at all. I'm just going to simplify what I need to here. So I'm going to go 1/3, and I'm going to write now the log base b of m squared as 2 times the log base b of m minus the log base b of n, and I'm going to leave it just like that. That is beautiful, and I have this expression, which is kind of ugly, in terms of simply the log base b of m minus the log base b of n. So that has answered the question. Now part B. Well, you see something times something, a log base b of m squared times n cubed. So I'm going to use number 1 there. I'm going to write that the sum of 2 log base b's. And on the left I would have the log base b of m squared. And on the right I will have the log base b of n to the 3rd. And then we use number 4 to bring these exponents out front. So we have 2 times the log base b of m plus 3 times the log base b of n. And there we go. Number 11. Great problems. When you show me you can do all this stuff, you are showing me you have the laws of exponents, the laws of logarithms down, and you have all your growth functions down, which is really, really important. All right. Let's solve a logarithmic equation where your logarithmic equation is base 5. Now, my first thought is I don't want the sum of 2 log base 5 numbers on the left there. I want that to be 1 log base 5. So, right here again, number 1, here it is again. Can't I write the left-hand side of this equation as the log base 5 of, and like here's my m and here's my n, I just multiply those, x times x minus 4, well x times x would be an x squared, and an x times negative 4, minus 4x. Oh, look at that now. Now with that one, log base 5 right there, I can just do definition of logarithm right now. Doesn't this mean that 5 to the first power has to equal x squared minus 4x? So definition of logarithm. So this base 5 to the first power has to equal x squared minus 4x. And now I have a quadratic equation that I can easily put into quadratic form by subtracting 5 from both sides. So 0 equals x squared minus 4x minus that 5. And now solving quadratics, well, I'll bet that's factorable. X times x, and I need a product of negative 5 and a sum of negative 4. How about a minus 5 and a plus 1? So by the zero product property of algebra, which we have been talking about all year, you guys right now are going to tell me that x could either equal a 5 or a -1. And a lot of you will say, I'm perfect, I'm done. But you have to remember one very important thing. This was not a quadratic equation where, quadratics are defined for all real numbers. This began as a logarithmic equation. Okay, so remember, your y equals the log base b of x. The domain of a logarithm is positive real numbers. There's no negatives here, so see that -1? That is not going to work. So I'm going to say x can only equal 5. All right, so always think about when you're solving these very complicated logarithmic and exponential equations, think about, are there any domain restrictions when you put your final answer on the board? Okay, number 13. Between what two consecutive integers must the log base 5 of 21 lie? All right, hey, my pupa's back at the door. She will just sit there and bark, so I'm going to go let her in, and we'll get right back to this problem. Come on, Rox. What? I know you just wanted to drink of water or something, didn't you? Okay, go ahead, go back to bed, and get away from my lunch there. No. Okay, let's try this again. So, again, nobody expects you to be able to give us a really good approximation of the log base 5 of 21, but you should be able to tell between what two integers that log base 5 of 21 lies, if you understand the definition of logarithm. Okay, remember, what's this asking? 5 to the what power will give me 21? Well, if you think of it like that, okay, what's it going to be? I need two consecutive integers here. So I'm thinking to myself, well, isn't 5 to the first power 5? And isn't 5 to the second power 25? And isn't 21 between that 5 and that 25? That means my x would have to be somewhere between 1 and 2. And obviously a lot closer to that too. So there we go, part A. Between what two consecutive integers must the log base 5 of 21 lie? Well, because 5 to the first power is 5 and 5 to the second power is 25, then this log base 5 of 21 would have to be somewhere between 1 and 2. And now they're asking us to find that to much more accuracy using the change of base. So use the change of base theorem to express the log base 5 of 21 in terms of common logarithms, and then evaluate to the nearest thousandth. So they're asking a little more there. Okay, so now when I do change of base, I usually use natural logs, but they've asked me to use common logs, so I'll go ahead and do that. I would typically go the natural log of 21 over the natural log of 5. But they want common logs, so we can do that. How about the common log of 21 over the common log of 5? And then I get my calculator out, and I punch this out. Common log of 21 divided by the common log of 5. And that is going to be approximately just what we thought. I'm getting, and they wanted that to the nearest thousandth. So that'd be 1.892 approximately. 1.892. And exactly what we thought. That would have to be between 1 and 2 and much closer to 2. All right, number 14. Now, this is what logarithms are all about right here. Solving simple exponential equations. Like 5 to the what power is 8? Well, you guys could approximate that. 5 to the first is 5, 5 to the second is 25. So we could approximate that. But what if we need more accuracy? Well, what is the inverse of an exponential? A logarithmic. All right? So how about we just take that exponential equation and let's take the natural log of both sides. There you go. Now, why? Because now with the laws of logarithms, this exponent can become a coefficient out front. So I have x times the natural log of 5 equals the natural log of 8. And now I just divide both sides by the natural log of 5. So x equals, and I've got the natural log of 8 over the natural log of 5. And I'm going to punch that out carefully. So let me clear this other stuff. And let's go the natural log of 8 divided by the natural log of 5. And I get 1.292029674. They want that to the nearest hundredth. 1.29. There you have it. Okay. By the way, what if I had taken the common log of both sides? Okay, that would have worked. Watch when I punch out the common log of 8 divided by the common log of 5. Guess what I'm going to get? Exactly the same number, 1.2920299674, or approximately to the nearest hundredth, 1.29. Well, this is good stuff. I hope you guys are enjoying them as much as I am. I think the review might be over. Let me double check. It is. So, you guys, make sure you come into, when we go over this, know exactly what you still have questions on, and let's get those questions answered. All right? Wishing everybody a great day.